Now, for the model of the machine, we'll have to spend a little more time on a little detour and look at how we can represent the computers we actually have, but also abstract them to something that is common to all of them. Okay, so this is the delicate part. We want to try to keep a model that's abstract enough so that we can analyze it, but still capture what is the essence of the computers we can build or that you can buy. And the RAM model, the random access machine model, is the consensus model of this to this date. And to motivate this, let's do this little question. So over to Slido. And the question is quite simple, right? It's a computer, so it should be able to add numbers. But how long does it actually take to add two numbers? I'll give you one more moment. Always the question that sparks discussions. Now I should have paid attention where we had before. We had 57 votes on the last question, 47 on the first. Maybe we can get a few more people.
Are we assuming constant word size?
That's the trick, yeah. So you're quite right. In a sense, the question is ill-posed, but that's only for those who thought about the right model. Let me lock it now. And I would say there's different answers that all make sense. Okay, no idea what you're talking about is correct too, but that's basically correct because I know you're coming from very different backgrounds. There's definitely two things that you can say that both make sense, and they seem to completely contradict each other. You can say constant time, which is true if you have integers that fit into one word. As one of you said, today's computers usually have 64-bit words. Most of them have. And so if you have an integer that fits into 64 bits, then you can add those two in, well, roughly one clock cycle. It's probably not quite true, but there's pipelining going on, and there's in a constant number of clock cycles for sure. And maybe the definition of what exactly is a clock cycle is a little less clear with the complicated architectures. But that is correct if it fits into one word. If the number is vastly bigger, as for example in the case of some cryptography, some crypto applications like RSA, where you need really, really big integers, then it's rather proportional to the number of digits. In a sense, it could be even worse. If you, for some stupid reason, decided you want to represent your numbers as unary, so the number of, you represent them just with a sequence of ones, and the number of ones is as long as the number you want to represent, then the answer would be exponential in D. No one does that, so it doesn't really make sense to put it up. But yeah, there's different answers to this. And they all kind of make sense. So how can we possibly have two answers when they contradict each other? So the reason is that we need to somehow let our model know how big the integers are, right? Let's go back one step. The machine model itself, what does it do? It not only tells you how things are computed, but in a sense, it also dictates what our algorithms or what programs for this machine look like. And so that's essentially defining what are algorithms for this model. It can usually describe how these are written down. And then you can allow something like pseudocode to abstract from that, but you could, in a sense, work directly on the language of the machine. So the machine model also describes the programming language in a way, the lowest level at least. And it usually defines a cost model. This is a little more subtle, but if you think about it, it's quite clear. The machine has some way of executing code, and that implies there's some time it takes to execute code, and that depends on how the machine operates. So the machine model also defines what is running time. I've talked about this trade-off before. We want it to be detailed so that it captures what's going on in certain machines that we want to use in applications at the end of the day. But we want it to unify what we have, where these machines differ. And ideally, it should also be simple enough so that we can mathematically analyze it. The real answer is there's more than one model that try to strike a different balance between these. And we'll try to stick to one that's closer on the simplicity side. That makes it easier to analyze it, but sometimes misses out some things. I'll point out some of these when we get there. And so without further ado, here is the model. That's the random access machine. And I want to briefly go through what it looks like. Again, we won't really build on this at this level of detail, but I want to make sure you know about it, because this question about how long does it take to add two integers, it is very cleanly answered in the word RAM model, and in any other model I've seen before, it was still kind of fudgy and not quite well defined. So we assume we have an unlimited memory, which is essentially one big array. So you can say there's a first cell, 0th cell, first, second, and so on. And you can use as much memory as you want. You will have in a way to pay for it, but there's no fixed limit. Now this seems a weird model, right? We can't really build an infinite machine. What we do have in machines is the option to extend them as you go. So you can think of whenever you run out of memory, you order more memory and attach it to the machine. That's still not really infinite, but this is also not what it says. It says it's unlimited, which means there's no fixed limit. That's not the same as infinite right from the start. We'll have registers. These are just variables that can store an integer, and we'll have a fixed number of those. I don't want to put a specific limit on those because it's often convenient in a program to assume you have a few more if you need a few more. You can think of it as around 100 or so in current CPUs. It will be convenient to say we can borrow a few more if we want, but it should not depend on the input size. That's the important part. It's fixed. Now, what can these registers and the cells in the memory store? They each store a W-bit integer. So that's the important part. It's not just any integer, it's an integer of a certain size with a certain number of bits. And the W itself is a parameter of the model that you have to kind of specify for the machine to make sense. We'll assume that these are just positive integers, but you can redefine things in your program to pretend they're also negative. So this is the basic model, and then you can make your program work with it in any way you want. What can you do on this machine? Basically 3 types of operations. You can load or store a single cell from or to a register. And it's important to say here that the location in memory from which you load or to which you store a value is also taken from a registry. So you can do something like indirect addressing. The address where you go to is taken from another register. So your program can compute the address. Then on the registers, we can compute. That's the actual computation going on. We can add numbers and all the other arithmetic operations. It's all integers, so keep that in mind, that something like division only makes sense in the integer sense. So you round down or you take the remainder. And all arithmetic by default is modulo 2 to the w. So this is what actual machines do. It's exactly taken from how CPUs work. And it's not usually a problem. On top of these arithmetic operations, we also allow bitwise operations. I don't think we ever use this in this module, but this is part of the word RAM. So you can do bitwise and or XOR negations, which allows some extra tricks sometimes. And the third type of operations is control instructions in your program. You can jump to a different location in the program, and you can make that jump conditional on some register. So you can ask, if that register is 0, jump here, otherwise don't. That's all you can do. The cost measure is quite natural, I guess. It's just the number of executed instructions from these 3 classes. And that's all you can do. So that's quite close to what current CPUs are like, except for one little weirdness that I skipped over. And that's this statement. So remember, n is the size of the input, size of the data you want to work with. And now this statement says, so this symbol is taken to be proportional to. So this says the number of bits in a single word grows with the input size. That's probably a weird concept. So let me write this down. You would think this is not really what computers do. They don't somehow just double. However, if you look historically on different computers, how the word size has increased, it's not so far from this. It's actually quite well described by this relation. Word size is roughly the logarithm of the input sizes. It just happens to be maybe the other way around. If you have a certain word size, you can work with a certain size of data, but this is not, it's not automatic. It's quite striking that this matches the historical development. So the machine grows with the input only means as a model. You can make the input bigger and bigger. And then if you need to work with inputs of a certain size, you would have to build a machine with the appropriate word length to do an algorithm properly. And there's another more intuitive reason, maybe, if you want. Think of n as the number. You're given your input is one big list, an array. Then that would take up n input cells. So what that condition then means is you can describe one position in this input in a single word. That's the condition we want. Maybe that's some somewhat intuitive condition. Okay, for now, take it as the definition, and in case of doubt, this is what you should look at for asking the questions. What is the actual running time? And so again, our question about how much time does it take to add 2 integers, it is proportional to d if you have d digits divided by w, because you can work on w digits in one time step. So if originally your numbers were small enough so that a constant number of words can hold them, addition takes constant time. If they're bigger, if they take a linear number of words, it takes linear time, and so on. So this model clearly answers that question without any resort to if this is the case, then this, and if that's the case, then that, and in between, I don't really know. You can imagine how if you program a RAM with these 3 types of instructions, this is very, very low level. It almost is like an assembly code for some actual processors. So this is quite inconvenient. What we usually do is instead write pseudocode. So that's code that's supposed to be clear enough for an average programmer to turn it into the description that the machine can understand. Now, average programmer, who knows what that is? But I'll just make some assumptions about our average programmer, and we'll have to live with that. The second simplification we'll make is, instead of counting the exact number of instructions on the RAM, we'll count dominant operations. And that's a bit problem specific what that means. But for example, it could mean the number of array accesses. The idea is that the overall running time will be proportional to the number of these dominating operations. And you will have to find what operation that is. And again, in many applications, it's quite clear what is a suitable choice. The important thing here, I want to stress this again, if you have this abstract model, in both cases, you can go into more detail if you ever wanted. That's the idea. You should always be able to. If you have pseudocode, you could translate it to actual instructions on the word RAM. And you could, instead of doing the dominant operations, count the exact number of instructions on the word RAM. It's inconvenient, it's tedious, it's often not needed for getting the statement you want, compare algorithms and predict how long they'll take roughly, but you could. That's the beauty of the detailed models. Before we continue with asymptotics, questions about word RAM, and is everybody clear about the D-digit addition now? So this might be something I want to put on the slides. I said this before, but didn't write it down. How much time does it take to add 2 D-digit numbers on a W-bit word RAM? Does anyone remember and wants to tell me? D over W, because I can work with W digits at a time. And remember, W is not a constant. W depends on the input size. So W can be log n. If D is well, it depends what n is. But this can be anything between constant and linear in D.